Does a selective loss of face recognition imply that a specific face recognition system exists in the brain? It sort of does. It's suggestive. But there are other possible accounts. Remember, the strength of a scientific inference hinges on whether we can come up with a different account. So here's this person. She's clearly smart. She's articulate. She's able to talk about her experience. She can see most other things, but she can't recognize faces. Does that necessarily mean that there had to have been a special part of the brain just for face recognition that was damaged? What else might it mean? Absolutely. I wasn't thinking of that one, but that's absolutely true. It could be just the wires coming out of a face region that got blitzed. Absolutely. What else? What else might that region be doing? What else might this person be missing? Maybe faces are just one of the hardest things we recognize. Maybe if you have a generically messed up visual recognition system, face recognition is the first thing to go because it's the hardest. Everybody get that? So this evidence doesn't nail it because maybe face recognition is just harder. After all faces have the same basic structure. And face recognition is arguably harder than distinguishing a car from a dog from a toaster because they look totally different from each other. They have totally different structure. Whereas the problem with face recognition is taking all these things that have the same basic structure and distinguishing one from the next. Does everybody see how that's an alternative account? And compelling as these data are, they are compelling, they don't totally nail it because we can think of these alternative accounts, the ones you guys came up with and the more standard one that people worry about in the literature. And in most cases, you should always ask yourself this question when you see evidence from selective brain damage, is this just a particularly difficult task? And that's why it's the first thing to go. So we have this problem. We have one case, actually quite several dozen cases in the literature of people with this selective deficit. And we want to make an inference, and it's a pretty good inference, but it's not a totally solid, watertight one because there are alternative accounts, particularly maybe face recognition is just difficult. Okay, so what are we going to do? The strongest case comes when we have other patients who have the opposite syndrome. Okay? If we could find somebody who is totally normal at face recognition, but really bad at recognizing objects, does everybody see how the combination of those two cases would just rule out generic difficulty? Because if face recognition is harder than object recognition, then you'd never get the opposite. So this is the power of something called a double dissociation. It's when in the literature, the neuropsychology literature of studying patients with brain damage, you have two different kinds of cases. People who are screwed up at A but not B, and people who are screwed up at B but not A. When you can find examples of both, that's a double dissociation, and it's very, very powerful because it rules out a generic difficulty account and lots of other accounts as well. Everybody get that? Okay, so there are basically two cases in the literature of the opposite. The strongest one is patient CK, and patient CK is a really amazing example. He's severely impaired at object recognition. If you show him line drawings, he's above chance, but really bad. And yet he's 100% normal at face recognition. In fact, he's a little bit better than your average subject. And if you think about that, that's pretty weird and pretty surprising and deeply informative. It's informative in part because if you think about the standard intuitive idea about face recognition, if you don't think about it too much, is you think, okay, you start with an eye, visual information comes in, you do some kind of shape, visual processing, and that works for most objects. But then maybe face recognition is really hard, and so it's a separate system that of extra processing you have to do after all the regular processing you have to do on objects. Right? Does that seem intuitive? Like you do generic shape processing, but then if it's a face, it's a special difficult thing, you have to do more? Well, the case of patient CK says this intuitive idea is just wrong. You could not get a case of a patient who's 100% normal at face recognition and severely impaired at object recognition if that's how the system worked. If face recognition was an extra special thing that sits on top of and requires input from your generic visual recognition system. Everybody get that? So this is a very, very powerful case in terms of what we can infer about the structure of the system, right? Okay. Interestingly, patient CK is 100% normal at recognition of upright faces, but he's really, 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 really bad at recognition of inverted faces. Much worse than any of you. What do you think that means? A reasonable inference is that the way we all process upside down faces is mostly not through our face system. It's through our object system, which is screwed up in CK. So he's just completely hosed when he's confronted with an upside down face. Everybody get that? Cool, huh? It actually turns out that's probably not exactly the right account, as we'll get to some data later, but it's a cool inference. Okay, so main point is it's the combination of these two opposite patterns of deficit, a double dissociation that's super powerful in inferring the functional organization of mind and brain. Generic advantages of Lesion methods, especially double dissociations, compared to other methods in cognitive neuroscience, they give us this very strong link between brain and behavior. They're evidence that the region that's damaged plays a necessary causal role in the function that you're testing. Okay, unlike functional MRI or ERP or MEG or lots of other acronyms. All right. But there are lots of disadvantages too. One is we can't just order them up, or we could, but it would be unethical, right? We have to wait for a patient to come along who has a particular kind of brain damage that might be informative to us, okay? And we can't choose where the damage is. Also, although I talked to you about cases where there's brain damage and a disrupted function, the opposite inference is difficult. So if there's brain damage and the function is still preserved, at least partially, we can't infer that that region was not playing a causal role before, because maybe there's been compensation or reorganization. Did you get that? So there are ambiguities in the inferences you can make from lesions. Also importantly, usually when a patient comes along, you don't have data from them on your task that you care about before their brain damage. So maybe these two people, it doesn't look like it from their testimony, but maybe these two people are faking us out and they couldn't recognize faces before their brain damage, right? Or maybe they were worse than usual, or maybe they were different in some way, and it's very hard to tell. And the thing that I mentioned before, usually the damage is not small and focal in the brain, and usually there are many disrupted functions, and so it's hard to make the inference about exactly what the function of each region is. Okay? All right. Right, and as somebody, I have a spatial cue, I forget who, pointed out, it could be fibers, was it you, Lauren? Yes. It could be fibers of passage going through that region, not that processor itself that was knocked down. So there are many ambiguities. It's a really informative method, but there are many ambiguities. Okay, now let me point out something else. I talked to you about cases of dissociation, somebody who is impaired at face recognition but not object recognition, or vice versa. Suppose a neurologist calls you up and say, hey, I have a patient who's screwed up at both object recognition and face recognition. Can you infer from that those two functions share brain machinery? That's called an association. Unlike a dissociation, it's an association. One lesion, two disruptions. Anna Marie. Where's Anna Marie? Yes, you were going to answer anyway, weren't you? So what can we infer from an association? Here's a patient with brain damage, and they've lost two functions, say face and object recognition. Does that mean face and object recognition are processed with the same mechanisms? Right, so if somebody has brain damage, as I said, the damage is usually big, usually knocks out a bunch of functions. And that produces an asymmetry in the power of the inferences we can draw. If you've got a dissociation, a person can do A, not B. That's pretty good evidence they're separate. Even better if you have a double dissociation. But an association, where they can't do two things, who the hell knows? Maybe two brain regions were knocked out. Maybe 25 brain regions were knocked out. Okay? So this point, I think, is pretty simple, but lots of my colleagues don't get it. There are people who publish papers saying, we have all these patients and they can't recognize faces or objects. Therefore, face recognition is not a separate part of the brain. Senior tenured professors at major universities write papers saying that. What? Okay, they may get away with saying that, but not in this class. We don't say that because it doesn't make any sense, because dissociations are more powerful and, in a sense, trump, sorry to use the word, associations. Everybody get that? One neurologist put it like this: association proposes, dissociation disposes. What that means is if a patient comes along who has two associated deficits, it suggests that maybe there's common machinery. But then if another patient comes along who's missing one and not the other, that disposes of that hypothesis. It trumps the earlier inference. Okay? All right. All right, so there are all these disadvantages. Not so great. What are we going to do? We're going to complement this method with other methods. And in particular, we're going to complement it with methods that enable us to have a little more control over the experiments. Instead of just sitting around waiting for these amazing data to come along when somebody has a very unfortunate occurrence, we're going to seize control.